So this, yeah, this way you learn supersymmetry before I start the superstring, so it makes more sense. Okay, so let's construct the spectrum, and let's start by the open string. So yesterday we said that we construct the spectrum, so the states in the spectrum are constructed with acting with mu1 minus n1, mu2 minus n2, with a bunch of creation operators on the ground state, and the creation are the ones that have negative n. So up to alpha mu j minus n j. And one can put a polarization tensor, and we'll see the symmetry. So we'll start constructing the spectrum for a few alphas. You'll see the procedure, and in the exercise you have a little bit more, but you see that it's technical. I mean, it becomes heavier and heavier technically. But there's no problem to do it. And so this is, in general, the states, but we have to require the physical state conditions. That I probably didn't call them like that, but it was basically, so the classical constraint that the energy momentum tensor is equal to 0, so in quotation mark, because this is a classical thing. We expanded this in modes. We call, or let me put the alphabet. So this was the sum of Lm e to the minus 2im for the open string, 2im sigma. Well, I hope this 2 is okay for the open string. And then what we require, so the energy momentum tensor, so sorry, this was the T plus plus, and this was sigma plus, but in the, so in the open string, that's only because of the boundary condition, T plus plus is actually equal to T minus minus. In the sense that there's a single set of oscillators. So Lm is 1/2 of the sum from n equals minus infinity to infinity of alpha m minus n contracted with alpha n. And in the closed string, we will have Lm, well, we have Lm tilde with the alpha tildes, but in the open string, there's a single set of oscillators because of the boundary conditions. And so the physical state conditions are Lm phi equals 0 for all m greater than 0. So the requirement was that Lm, so the sandwich, so the requirement was this, equals 0, and then since L minus m is the dagger of Lm, it's enough to require this. And let's see what happens with L0. So when m is not 0, alpha m minus n commutes with alpha n. So you can put this, you can put these two in the order that you want. But when m is equal to 0, these do not commute. So we have to be more careful. And let me call, so the question is, what is L0 and what happens with these commutators? So let me call, so Lm for m equals 0, let me call that L0 hat. Because L0 will have, so for L0 will absorb this commutator. So this is by definition L0 hat, and it just corresponds to putting m equals 0 there. So this is a sum from n equals minus infinity to infinity of alpha m minus n, alpha minus n, alpha n. And now let me split the sum. So this sum is when n is equal to 0, so 1/2 of alpha 0 squared. And I always want to put annihilators on the right. So when n is positive, this is an annihilator, so I leave it like that. And when n is negative, I will write this as a commutator plus the alpha minus n on this side, but minus n now is positive, and that will be an annihilator. So I have two terms. So I have the sum from n equals 1 to infinity of alpha minus n, alpha n, right, by putting alpha n always on the right. And then I have the commutators of alpha minus n and alpha n, and that's equal to, so minus n, but n is negative, so that's equal to the sum n equals 1 to infinity, so 1/2 of the commutator of this, which is n, and then the zenita mu, right? Because this mu is contracted with mu, and in the commutators you get an eta mu nu, so this is what we get. And let me not write, so this would be d, but let me not write d for the moment. Now this is obviously infinity, but we're going to, so this is the only renormalization that one does, and I will do it towards the end of the class. So this is actually, so I will write something and then I will erase it, I won't leave it. Did you know this? So we'll see this, you get it from zeta function regularization, or there's Riemann zeta function, so Riemann psi function regularization. There are different regularization schemes and they all give -1/12. And that's the only regularization you have to do ever. The rest of the things are finite. So, okay, so I'm not going to put explicitly what this is, but this thing, this constant, that it's infinite, but it will be regularized, is called -a, just by definition. So this is by definition. So L0 is 1/2 of alpha 0 squared, and alpha 0, if you remember, alpha 0 was square root of alpha prime over 2 p mu, the center of mass momentum. So this is alpha prime, alpha 0 squared is an alpha prime over 2, so this is p squared over 4, and then alpha prime. Plus the sum n equals 1 to infinity of alpha minus n, alpha n, minus this constant a, that is this 1/2 of -1/12 and this, but yeah, I still have to explain something about this. So for the time being, this constant is -a. So this is this L0 hat, which is which is just L0 when you put m equals to 0. Now it's useful to, you will see why. So I'm going to define this to be my L0. I don't like this constant here, and you'll see why. And I want to define this to be L0. So this is by definition L0. So L0 and L0 hat differ by this constant. So the physical state conditions one more thing is that it's not hard to see that L0, if you do the Hamiltonian, which is, so x dot mu p mu, where this big p mu is the one I defined yesterday, the derivative of the Lagrangian with respect to x dot mu. So minus the Lagrangian, and you have to integrate over sigma. That's the Hamiltonian. It's not hard to see that this is the zero mode of the energy momentum tensor. Well, and also, I mean, it makes sense that the Hamiltonian is a zero mode of the energy momentum tensor. So this is actually 1/2 of L0. No, it's 2L0. So the Hamiltonian is 2L0 hat, 2L0 hat. So this A here is related to the 0-point energy, the quantum energy of a state, because this gives the center of mass. Yeah, so this gives the center of mass momentum. This operator here, I'm going to call it n. And as you will see, this counts the number of oscillations that you have. So this will count, if you have a state like that, the eigenvalue of this operator n will be n1 plus n2 plus nj. It's not very hard to see, and we'll see it in one example so that you get convinced. So 2 times L0 hat is alpha prime p squared over 2 plus this operator n minus a, minus 2a, and 2n, right? But so this a, this minus a, you see that this is a 0-point energy, so what we call E0 over 2. So it's a 0-point energy of the quantum of the vacuum, this minus a. Now, that we will compute, but you see, so that sum over n is negative. So with this minus sign means a is positive, so minus a is negative, so the 0-point energy will be negative, and that's basically why we will have tachyons in the bosonic string. But okay, I'm going a little bit ahead of myself. So now going back to the physical state conditions. are Lm phi equals 0 for all m greater than 0. And el 0 hat phi equals 0 because, sorry, I forgot to say something. Okay, let me finish this and then. El 0 hat phi el 0 hat is the one that should annihilate phi because the mode of the energy momentum tensor is el 0 hat. So in terms of L0, what I have to require is that L0 phi equals this constant phi, right? So this is equivalent to L0 hat phi equals 0, which is what we should require. L0 hat is the real zero mode of the energy momentum tensor. And why do we need to do this? I mean, this is useful because now there's an exercise to compute the commutation relations of these LMs. Can I erase this? So it's exercise. Yes, sorry. Yeah, because L0 hat is a real mode. L0 hat, so Lm are the modes of the energy momentum tensor. When m is equal to 0, that's L0 hat. Then I define L0 to be L0 hat plus A. So this is, yes? Okay, yeah, sorry. So this is, yes, so this is a definition. And why is that? So the actual zero mode of the energy momentum tensor is this L0 hat. And I define L0 like that for convenience. So L0 is not Lm when m is equal to 0. It's not that. But why do I do that? This is because, so there's exercise 2.8 and 2.9. To compute the commutation relations of Lm and Ln, which are, okay, that part is easy to get. What is hard to get is this, so it's some constant. This is the part that is hard to get. This is called the Virasoro algebra. And here you see that the nice thing of reabsorbing, if I didn't absorb this A in the definition of L0, then I would have it here. So the nice thing is, so L1, L minus 1, and L0, for L1 and L minus 1, for the commutators of L1, L minus 1, and L0, this term goes away. So they form a closed algebra, L1, L minus 1, and L0, and that's a very important algebra in conformal field theories, translations, rotations, and conformal transformations. So that's why I wanted to absorb this constant I. Well, that's why usually, so one absorbs this constant in the definition of L0. So let me write it here because in case so L0 hat, so or L0 is equal to L0 hat plus A. And once I do this, then you have this algebra. This term here is called the central, this constant C here is called the central charge. And it's central charge because this algebra doesn't have, so the usual form of an algebra is commutator of operator and operator equal operator. But here you have commutator of operator, operator equals operator plus something times the identity operator. So this is like a centrally extended algebra. That's called a centrally extended algebra, the term that has the identity as operator. So this is like the central extension, and that's why this is called the central charge. And there are lots of things to say about that if we really saw conformal field theory, but we're not. But with Alimil Masak, you're going to talk about this central charge for sure. So here for the x mu, so for the free scalar fields, as this is the conformal field theory that we have, C is equal to D. So one free scalar field has C equals 1. So our central charge of the system is C equals to D. A collection of the free scalar fields, which is in two dimensions, right? So for the free scalar fields in two dimensions, so all we're doing is conformal field theories in two dimensions. Then C is equal to D. So my x mu are free scalar fields from the point of view of the two-dimensional theory. Yes?
So doesn't it show why we can't do like LM and L minus M?
Yeah, exactly. From this you can see precisely that you cannot require Lm and L minus n annihilating the vacuum at the same time because you have this central charge term, which is associated, which is related to the 0-point energy. I mean, there was a 1/12 in the sum, so in the sum of n equals 1 to infinity of n, (9/12). So this 1/12 is related to this 1/12. Here there's a d, but I didn't want to. So all those things are related, and this is why, yeah, in the quantum theory you cannot require that m positive and m negative annihilate the physical states.
Sorry.
Yes.
From the definition of A,
Uh-huh.
if you put eta mu to be D, then the sum is just what the term is D over minus D over 24. But we know that D is equal to 26, so A is not 1.
Yeah, so that's why I didn't want to put this to be D. So we will discuss this because you have to put real physical states, and so you have to subtract. So I will say that, yeah, but good. That's why I didn't want to put D, because, yeah, I'll say about that.
Sorry, D is indeed the dimension of the space-time.
D is a dimension of the space-time, yeah. We have D free scalar fields, yeah. So we have the x mu, these are the free scalar fields, and mu goes from 0 to D minus 1. Yeah. So for one free scalar field, so we are in flat space, we're doing everything in flat space, so the Polyakov action is just the derivative dx mu, so these are free scalar fields. And then they have C equals 1. Each of them has C equal 1. Yes? It's exactly the same for the closed string, but you have a double set. You have Lm and L tilde m. So yeah, maybe I shouldn't have said open string. So this is general. What's particular about, so in the closed string you have the alphas and the alpha tildes. You have the L and the L tildes. So for the left and for the right. But they satisfy the same algebra for the closed string, the L, and so, good, thanks. So for the closed string, we have the Lm and the L tilde M. So L tilde N is the same as, so it's, I mean, it's this with L. I remember it's easier to write it. So M minus N, L tilde M plus N, plus exactly the same. So C over 12, M times M squared minus 1, delta the M plus N 0. And because the alphas and the alpha tildes commute, Lm with L tilde N is equal to 0. L and L tilde commute, okay? We have two copies of the algebra, yeah. One for the left and one for the right. If you do complex coordinates, as we defined before, so one is for the holomorphic part and another is for the anti-holomorphic part. Yes?
I guess another question about how you can see that neither the right has real estate conditions to impose. Like we could have also thought about imposing some smaller subset, right?
I mean, what you want is really that the energy momentum tensor, this is equal to 0. And for this, then it's enough to, it's necessary and sufficient to require that for all M, I mean, to require, so these two things. But yeah, we cannot require a smaller set of constraints. Yes? This is for normal order operators, yes, but yeah, here there is no much. I mean, the only this for Lm with M different from 0, you can order them as you want because they commute. And for L equals 0, we did. So this is L0 like that in that order. So, yeah, so the L0 hat is not normal order. The one that is normal order is L0. So, I mean, so there's the exercise. So basically what you get is that, again, so that part is easy to do. Let me, where can I write? Let me write here. So, if you do these commutators, Lm, Ln, what you get is this part, as I said, that's easy to L plus N. And then you get some constant. So that's how the exercise is. That depends on M, and then a delta M plus N 0. So these are the only ones that where you will see these non-trivial commutators. In the others, they are just, you can normal order them or. So normal ordering means putting the annihilators on the right. And for M different from 0, you can order them however you want. I mean, you can always do normal order, and non-normal order is the same. Here, the normal order thing is L0, where I put the annihilators on the right, and then I don't have this commutation, this part of the commutations. And then the other exercise, if I have it here, is to, I mean, then you can see let me see, how does it go? Yeah, so now if you do L1 and L minus 1, for example, what you get is 2L0 hat plus 2A. So then from here comes a definition. So so this by definition is 2L0. So, and so this you get, precisely as we got this constant A, you get that when you do L1 and L minus 1. And then this by definition is L0. And then you have to keep going to work to see that A of M has that form, M times M squared minus 1. And then the constant, so C is, C over 12 is like A of 2 divided by 2, I think. So then you just you can write everything in terms of A for some, so for M equals 2, and then that you call C over 12. That AM, of that form, once you absorb this in L0, then yeah, that's, it's not easy to see. So the first part of the exercise is very easy with seeing this, and the second part, but it's a little bit guided, the exercise, to see that that A of M has that form, is some constant times that form in terms of M and M squared minus 1. Okay, so now, now physical states and open string. Maybe I can start there. So, let's construct this spectrum. So we say we start with a. So let me start with this ground state. So phi equals. So I don't act with any creation operator. First, is it true that LM0 is equal? So first, as I said, this 0 is such that alpha mu m on 0 is equal to 0 for all m greater than 0. So it's annihilated by all the annihilation operators. Now, is this true? Well, this is easy to see because when you come here, when n is positive, it will annihilate this. And when n is negative, you just put it the other way around, and this is going to be annihilator. So it's very easy to see that this is true. And now I want to require the condition L0, 0 equals A. So the L0 phi equals A phi. That, of course, I erased, so it was one of the, so the other physical state condition. So L0 phi equals A phi. So L0, we have it there, is alpha prime p squared over 4 plus the sum from n equals 1 to infinity of alpha minus n alpha n on 0, so equals A 0. Now p squared acting on this is going to give me back so I can call this 0. 0, I can call it 0k, which means it's moving with some center of mass momentum that I call k, or I can call it p, but just it's usually called k. And this way to distinguish p operator from its eigenvalue that I'm going to call k. So this is just alpha prime k squared over 4 times this. Now, this is obvious that this annihilates the state, right? And so I just have to require that this is equal to A, right? Now as an eigenvalue equation. And this is a requirement. So I'm going to require that this state is on shell. So k squared is equal to minus m squared. So what this is, and I shouldn't have the 1 over 4. What? What did I do? Sorry, this should be alpha prime p squared. I missed. So 1/2 of alpha 0. I see, so alpha 0. I think I put the p squared over 4. So alpha 0 is p square root of alpha prime. And then alpha 0 squared is p squared over 4. Well, I have a factor of 4 wrong. Sorry, and I don't know, I don't see where now. Okay, so this should be like this. Let me check where the mistake is. Maybe it's in the definition of alpha 0 mu, which doesn't have the factor of 2 in the, okay. So, sorry, should not be there. So, for the open string, this should not be there. Sorry, that's, I mean, it would change the masses all by a factor of 4. It doesn't change the physics of what I'm going to say, but yeah, they should be like that. So then this is saying that m squared of this state is minus, so 1 over alpha prime, or minus A over alpha prime. 1 over alpha prime times minus A. And we said A is positive because of this, because of this minus sign and that minus sign, A is positive. And as somebody said, A is going to be equal to 1, but so this means that this state is physical. I mean, if it satisfies this mass shell condition, but this is, I can say that this is the requirement. And it's a tachyon. So this state is a tachyon. So that's not good. States with negative mass square. So that means there's an instability. And that the true vacuum is somewhere else. So I have to do something with the tachyon. And we don't know what to do with the tachyon. So the bosonic theory. So this is saying, at the end of the day, that the bosonic theory is not a consistent theory. So it has this tachyon. It has this tachyon that signals that the theory is unstable. We don't know if, there's no, it's not that it runs to another theory where this tachyon is not there, so it's not consistent. But again, one starts from the bosonic theory because a superstring, which is a consistent theory, it builds from the bosonic string and adds supersymmetry. So that's why one starts from this. Yes. Yeah, you can think of that as there's a maximum of the potential. I mean, something with mass square negative is something where you have a potential. So the potential for this, I mean, one can think the potential for this state is something like this. So it's here. So that's a potential of minus a half, so m squared negative. So it rolls down to somewhere else, but we don't know what that somewhere else is. It's not, I mean, just keeps rolling if you want. Yeah. Yes, but whatever regularization you do gives you the same. Yeah, but it's not your choice. I mean, it looks like it's your choice, but I mean, I'll show you how this appears. And there are other regularization schemes which are a bit more complicated and more formal, like going on the complex plane, and they all give this minus 112. Yeah, I know this is not nice, but as I said, this is the only regularization you have to do, and then you compute loops, and it's not that every time you have to do some. No, so I mean, let me anticipate that. Maybe we won't have time to do this, but it's so. Well, yeah, okay. Just to. Uh, I mean, it's like, yeah, it's like doing a renormalization, but a single one with a single scheme. And well, I mean, with a single scheme, with any scheme you want, and it gives you the same. And it makes sense that that this 0-point energy is negative. And you build from that. I mean, the states, then as you keep going, now the states will be, I mean, that's the only state that has a problem. And actually anticipating, that will appear also in the superstring, but in the superstring we know how to get rid of that state, while here we don't. If that was negative, then it would be, if A was negative, it would be good from this sense, but it would be bad in the sense that everything will be massive, because this, I mean, this operator n will have positive eigenvalues. So everything will be massive and very massive, because this 1 over alpha prime is a string scale square, and everything will be very massive. Our theory will be useless, actually, to describe the real world. So it's good that this A is, I mean, it would be better this A to be 0, but it's, yeah.
Maybe it's a question related to another question. So typically in quantum theory, you say that every operator, you normal order the operator, that essentially you don't care about the commutators, and then you take the normal order. And here, this sentence would translate in A goes to 0. And then, okay, mass square would be 0 in that case, but I suspect, and maybe it's wrong, I don't know, that if you put A to 0, you have like a space-time dimension that is not is like 0 or something strange, or maybe if you put A to 0, you have lost in the theory, so that's the only way to. I don't know. Because otherwise, in QFT, you should put A. You could put A to 0, right?
I mean, it's not my choice. Again, it looks like it's my choice, but you regularize this, and what you get is infinity minus 112, and you get rid of the infinity. So it's the same as what you do in whatever way you do it, you get infinity minus 112. So yeah, it looks like it's my choice, but it's not my choice. Whatever you do, you get the same. However you regularize this, you get that result. So yeah, so it's not our choice to. This is not our choice. I mean, I understand this math, and I don't like renormalization either, and that's why I think quantum field theory should be completed. I mean, the standard model should be completed by some UV completion. But again, this is the only thing one does, the only renormalization one does. Okay. Let's go to the next step. The next, so these are called levels, and so the levels are given. So we will see that this in the next level. So this level is n equals 0, and because this annihilates that state, this operator n, the next level will be n equals 1. What you'll see. So I just put some oscillator, one oscillator, and with -1. So the lowest oscillation number I can put. So now Lm, or let me first do L0. So from the condition L0, phi equals A phi. The first term gives me alpha prime k squared, so up to this factor of 4, that should not be there. And now from this sum, let me write here n equals 1 to infinity, alpha minus n, dot alpha n, e mu, alpha mu minus 1, 0. It's easy to see that the only term that will give something non-zero is when n is equal to 1, right? All the others annihilate because I can pass this here, and it annihilates. So this is equal to E mu alpha minus 1, alpha 1, alpha mu minus 1, 0. And now I commute these two. Whenever this is on the right, it annihilates this. So the only thing I get is the commutator. And so if I write this as alpha minus 1 lambda and alpha 1 lambda, and I'm not careful about raising and lowering, but I can, if you want, I can be. In this commutator is going to be a delta of lambda mu. So this is E mu alpha minus 1 mu 0. So this is the operator n acting on phi. So n acting on phi, it gives me this, and this is phi, right? So this state has n equals 1. N as a, so I'm being sloppy between here is the operator and here is the eigenvalue. But it's easy to see, again, that this operator counts the numbers that you have here. So again, for a general state like that, it's going to give me n1 plus n2 plus, because you will have to commute every time, and when you commute, you get a factor of n1, then you will get a factor of n2. So n1 plus n2 plus nj. So this operator n measures what is called the level. So this next level is n equals 1. The one before was n equals 0, and this is n equals 1. So now if I go back here. So L0 was alpha prime, L0 acting on phi is alpha prime k squared plus 1 equals A, right? That's my condition. That's the condition L0 phi equals A phi. And again, k squared is minus m, so this is minus m squared. So this is saying that m squared is 1 over alpha prime, 1 minus A. And as somebody said, A is equal to 1, so anticipate. So anticipate, I mean, we have this, and the only thing that that I will have to convince you is that this has to be replaced by delta II, and this I are 24. So this gives a D minus 2. Instead of giving a D, gives a D minus 2. And if you plug in D equals 26, okay, I'm going a bit ahead of myself. Hopefully we'll be able to do it. But if you plug D equals 26, then what you get is A equals 1. So now let me anticipate. A equals 1, so this says that m squared is equal to 0. So this is a massless state. So this is a massless state. So phi equals E mu alpha mu minus 1, 0 is a massless state. And it's a vector, right? It has one vector index. So this is a massless vector. We like massless vectors, right? I like massless vectors. Do you like massless vectors? I mean, this. Anticipate, I put. Let me. So hopefully we'll compute that and you will see. Well, not completely, but for the time, yeah, for the time being, let me say A will be 1. We'll compute it and A will be 1. Okay, this is nice. This is very nice. But we haven't, so we just require the L0 condition. So we have to require all the LMs with m greater than 0. Now, it's easy to see that Lm phi is equal to 0 trivially for all m greater than 2, because the LMs are not written there anymore. Okay. Lm is 1/2 of the sum minus infinity. So this is for all m different than 0, alpha m minus n dot alpha n. And if I have, so for L2, this is 2 minus n. Whenever n is positive, this, let's do L2. Or maybe, I mean, all these exercises are much simpler if you do exercise 2.7, which is this commutator, Lm alpha mu n This gives minus n alpha mu m plus n. So this is very, very easy to get. So it gives me an alpha mu m plus n. So if I do L2 on this, I want to commute. Yeah, yep. Yeah, so I want to commute these two. So L2 Lm on phi is equal to the commutator, so E mu alpha mu minus 1 Lm on phi plus a commutator, so minus n, sorry. I'm commuting Lm with alpha mu minus 1. So this will be, so minus 1, so this will be plus alpha mu m plus 1 e mu alpha mu m plus 1 0. Sorry, this is 0. But we saw that Lm on 0 m minus 1, yeah, otherwise it wasn't. It was too easy. Good. So we saw that this is 0 for all m greater than 0. And this is trivially 0 for all m, so this is equal to 0 trivially for all m greater or equal than 2, right? For 2 I get an alpha 1. The only non-trivial one is m equal 1. So L1 phi is this, is E mu alpha mu 0 and this gives me, so, some number. I don't care, I have to require that this is equal to 0. So, E mu, K mu, right? This alpha 0 gives me a K. So, or the way to make this, so I want to make this equal to 0. So this tells that E mu, K mu should be 0. So I get a massless vector whose polarization is orthogonal to K mu. To K. So I have this K dot E is equal to 0. And now since it's massless, since m squared, which is equal to minus K squared, is equal to 0, I can take K mu to, so moving in the direction x1, so I can take it to be K 0, 0. So it's K is like, and let's put it moving in the one direction. Right, this is K squared equals 0. And so what this is saying is that E0, well, if I put it like that, this says that E0 plus E1 is equal to 0. write the polarization. So E0 is equal to minus E1. And then all this can be anything. All the E's. So E mu is minus E1, and then whatever. Let's write this as EI. So I goes from 2 to D minus 1. So this means I have D minus 1 possible polarizations. But this is not very nice. So how many polarizations does a massless vector have in 4 dimensions? 2. So D minus 2. So I don't like this too much. I would like to have D minus 2. So we will get D minus 2 after the 5-minute break. Questions about this? 5-minute break. So it's almost 20. So back at 23. Okay, let's go on. So before looking at this story of the polarizations, let me summarize what we have. So at level n equals 0, we have this 0. It's physical, its mass is minus 1 over alpha prime. So I'm using A equals 1 already. Then at n equals 1, we have, so this has m squared equals 0. And the condition is A mu, that this polarization is orthogonal to K. And then I can keep going. So what states do I have at n equals to 2? So I have alpha mu minus 1, alpha nu minus 1 on 0, and E mu nu. And this commutes, so this E mu nu should be symmetric, so it's a symmetric to tensor. And I have another type of state at level 2. Alpha minus 2. So I have this symmetric to tensor and this here. So these have m squared. So in general, this condition tells us that m squared is 1 over alpha prime n minus a, but a is equal to 1. So these have m squared equals 1 over alpha prime. And there's an exercise. It's good this exercise because it's to see the physical state conditions. So they are non-trivial. Actually, you have to, some of these states are non-physical, so I'm not saying, and so they have this mass. There are some physical states, but you need to impose Ln phi equals 0 for m equals 1 and for m equals 2. These two give conditions, and then Lm phi equals 0 trivially for m greater or equal than 3. Because of the erase, it gives you an alpha. When you commute, it gives you is going to give you an alpha 1 m, so m minus 2, and so from m greater than 3 is trivial. But these two give conditions, and you have to work it out, and you can keep going. The physical state conditions become more and more painful because every time you have to add another LM that gives you some non-trivial condition, but you can do it. And so what we get is a tower of states of mass. So if this is m squared equals 0, so unfortunately we get this tachyon, m squared equals minus 1 over alpha prime. M squared is 1 over alpha prime. M squared equals 2 over alpha prime, etc. And again, this 1 over alpha prime, it's a or 1 over square root of alpha prime is a string scale, which is 10 to the 10 GeV at least, up to the Planck scale, 10 to the 19 GeV. So these are very massive. So if you want to study any low energy physics, you stay, well, not in the bosonic theory because you have this tachyon, but forgetting for the moment in the superstring, you will not have this tachyon. So if you want to do any low energy physics, you stay. So in the superstring, we'll also have this tower of states, and they will be very massive. So if you want to do any low energy physics, you concentrate on this massless sector. And then the masses of particles, because we can embed the standard model in, I will say a few words of how. The masses come from other, like Higgs mechanism or things like that, but on the states which are massless. Because this is much larger than the mass of quarks, of mesons, or whatever we know. So everything comes, all the real where physics comes from this. But of course, these are very important, ADS-CFT, I don't know, there are many things for which these are important, this tower of states. And actually a theory with one massless state is not consistent, or with whatever d minus 2 massless states is not consistent. You need to have this tower of states to have a UV completion of the theory. But so now I will concentrate on the massless sector. So this is the one I'm interested in. And in the closed string, we will also look at this massless. And in the superstring, we will look a lot at the massless sector. Okay, so we said that from this condition, we get d minus 1 polarization. So the polarization tensor is like that if we choose k to be in the one direction. So like, but moving in the one direction. And this doesn't fit with what we know of massless vectors in 4 dimensions. So how do we recover these d minus 2 polarizations? And this is from what's called the, so this, so again, I'm at level n equals 1, phi equals e mu k mu on 0, sorry, not e mu k mu, that's 0, e mu alpha mu minus 1 on 0, e mu k mu equals 0. And at this level, one, or at every level, one can construct null states. And let me know what they are. Let me tell you what they are. So, I mean, null states are, so first I have to define the spurious states. The spurious states are states that satisfy the spurious states, how did I call them, chi, of psi. They satisfy this, so they are on shell regarding mass, and they are a spurious state at different levels, but not necessarily the other Lm psi equals 0. And then the null states sorry, I forgot something. So they satisfy this, but they are also orthogonal to any physical state for all phi physical. These are the spurious states, which are called descendants in the CFT language. And then we have the physical states, right, that satisfy. The physical states are the phi that satisfy Lm phi equals 0 for all m greater than 0, L0 minus A phi equals 0. Okay, so these states we saw. Now the spurious states satisfy this condition, but not necessarily the others, and they are orthogonal to any physical state. And now the null states are the states that are spurious. And spurious because, I mean, if you do any scattering process, you don't see them because they are orthogonal to any physical state. And in scattering process, you create physical states, then you're not going to see them. So that's why they're called spurious. And the null states are spurious and physical. So if I call them chi, what is the norm of chi? 0, right? Because it's spurious, so then it's orthogonal to any physical state, but itself is a physical state, so this is called 0, and that's why it's called null state. Yeah. Let me leave that. And again, these are if you have a phi at a given level and you create, let's create a phi tilde, which is phi plus some chi. Now, if I do any process, or if I take the norm, for example, of phi prime with any other prime, double prime, I don't mean derivative, I mean different states, or well, I don't know, let me call this phi tilde. With any state, any physical state, phi tilde, then this is equal to phi tilde phi, right? Because this chi goes away. It's physical, I'm allowed to put it, but I'm not going to see it in any process. So this is some sort of redundancy of the spectrum at a given level. So if you want to compute the Hilbert space of the physical states, you have to do, the real non-redundant degrees of freedom, you have to quotient by these null states, because these are a redundancy. You're not going to see it. And at every level, there are null states like that, and in particular at n equals 1. Can you think of a null state? You're still copying. And I don't want answers from people who saw this before. But what happens with this state? Is it physical? For it to be physical, so physical means the L0 condition, it will tell me that it's a state, it's a massless state. And the L1 condition was saying this, that the polarization along K should be 0. So K mu should be 0. But this is true because it's a massless state. So K squared is equal to 0. So this is, it's a physical state. And its norm is 0, right? Because K squared is equal to 0. So this is a null state. So this is saying that to any polarization, I can add another polarization. I mean, I can put some lambda here, some whatever constant. But if I have this, if I sum this K mu under this condition, that K squared is equal to 0, then I'm not going to see this part. So if we go back here, so our polarization in general was like that. And now this is saying, this implies that E, so I left it in terms of E1. So E1 is equivalent to E1 plus, or yeah, plus K. And I don't know, some lambda, I put that lambda. So in particular, I can choose then, choose this lambda to have E1 equals 0. And so my polarizations then, if E1 is equal to 0, then E0 is equal to 0. So I can choose a polarization to be, to have these D minus 2 components. So we have these D minus 2 polarizations, which are orthogonal to the light-like direction of K. So this is exactly what happens with a massless vector in 4 dimensions, where it has 2 polarizations which are orthogonal to K. So this object is the quanta of a field, massless vector. So let me call this a mu. And this relation here, if you go to the, if you do the Fourier transform, so if you do a mu So if you do a mu of a x to the I k e dx, so this is d dx to the I k x, having a k mu here is equivalent to having a derivative, right? And so this E mu equivalent to a E mu plus k mu lambda. For this gauge field, a mu of x says that a mu is equivalent to a mu plus the mu lambda. And of course you recognize this, so this a mu is a gauge field. So this states alpha E mu, so this phi equals E mu alpha mu minus 1 on 0. These are the quanta of the photon, this, I mean, a gauge field that has this gauge symmetry. Yeah. Now this is a U1 gauge symmetry. Maybe one can ask, can the gauge symmetry be non-abelian? So this is a U1 gauge field. I still don't want to erase that. And the answer is yes, but I'm going to pull it out of the hat now. And if we see the brains, hopefully, then you will make more sense of what I'm going to say. I mean, I guess we'll see the brains. I will just cut some things, but some basic things about the brains I would like to say. So the answer is yes, and this is via what's called Champaton factors. And these are, so the endpoints, so this is an open string. Its endpoints, I can assign some degree of freedom, that goes from 1 to, let's say, some number n. This n has nothing to do with the level, right? This is some n. And here, so this is in some fundamental representation of GLN, and this is in some anti-fundamental, because these are two different, so this is the sigma equals 0, and this is the sigma equals pi. So one I call it fundamental and another anti-fundamental. And so whenever an open string that is oscillating with n equal 1, so one oscillation, like this. So then I have to give these Champaton factors. So this means that the vector that corresponds to the vector, so it's oscillating in some direction E mu, right? Or EI. So from the point of view of the gauge field, so this is a quanta of a gauge field that has these indices, and this is a UN gauge field. And again, here, I'm pulling this out of the hat, but let me say, just a couple of words. I'll let you copy before I.
Sorry.
Yes.
A and B are just the endpoints of the string.
Yes.
So I don't understand the meaning of A then.
Of
A or B are.
A is some index that goes from 1 to n. So this could be 2, 3. I mean, let me say what I'm going to say and you will make more sense. The way to make sense of this that we pulled out of the hat is, so remember we had Dirichlet or Neumann boundary conditions for the open string. Suppose we have Dirichlet boundary conditions in this direction and Neumann in all these directions. So that means the open string, so that means, so I'm having, so this is, I don't know, this is what we call X0. I'm putting in, so let me call it X10, so this is the direction X1, and these are all the other directions, Xi. And I'm fixing the string to be at X01. And actually, this Dirichlet boundary condition, this corresponds to having Dirichlet boundary condition in one direction corresponds to having like a wall here that attaches the brane, and that wall is precisely a D-brane. So the open strings attach, they are attached to D-branes. The D-brane, so these are all the directions. So here you have Neumann boundary conditions along the brane, and here you have Dirichlet boundary conditions, orthogonal to the brane. And what this n index, sorry, this is Neumann, not the, and this is Dirichlet. So what this n index tells is that I can have n D-branes on top of each other, which if this is a wall, it doesn't, I mean, so what does it mean to have n D-branes on top of each other? It means something, so that this is not an infinitely heavy wall, but it will have some, it will be a heavy wall, but, so having n is not the same as having 1. So what this index is telling me is to which D-brane this is attached. So if I have indices 2 and 3, means that one end is attached to the second brane, and the other is attached to the third brane. But they are on top of each other. So I hope this is a bit more convincing that pulling this out of the hat. So then, so A tells me, so which one of the n D-branes, the endpoint sigma equal 0 is attached to, and this B bar tells me the sigma equals pi. So any open string, also the massive ones, will have this Champatton degrees of freedom. If they have all, I mean, they have all the x's, the embedding coordinates, are the ones that have this Dirichlet and Neumann boundary condition. So all the strings, if you have some Dirichlet and Neumann boundary conditions mixed, all the strings will have this A, B bar indices. So this UN, so this is in the adjoint of UN, and any massive string will also have that. And yes. Yeah, sorry. Yeah. This is not the level, okay. Huh? No, yeah, as it is, no. No. This is always, yeah. This is always in the adjoint of some group. The group doesn't need to be UN, so it can be SO to n, or it can be more complicated. So I will talk about SO to n, but yeah, it has only two indices. Yeah. Unless you do so. One way to construct the standard model is to put 3 brains here, 2 brains here, and then attach strings, and it will have, this will be in the fundamental of SU3 times SU2. So having brains at the intersection of these two. Yes. Yeah. It's like you have one brain, yes. Okay, so I'm done with the open string, and I was going to do the closed string up to the massless level, which is very short, but and then I was going to compute A. How energetic are you? Are you dead? Yeah, I see many people nodding. Yeah. Okay. Let me do. I mean, the closed string is easy. It's just the tensor product of open string, and you don't have this Champatton degrees of freedom, so it's not hard. So we can do that quickly in the afternoon, and then go on from there. Okay. More questions? So I interrupted the clap. I let you clap then afterwards. Okay, I'm here if you want to ask questions. That's a Q&A session.